When working with the likes of trigonometry or SOHCAHTOA, you have come across that you can find for a missing angle by doing the inverse of either the sine function, cos function, or tan functions. Again, that gets you probably the angle in a triangle. However, strictly speaking, each of these functions goes on infinitely, both into the positive and into the negative, meaning there are technically infinite answers to any given, like say for sine, a combination of opposite and hypotenuse. Obviously, this isn't going to necessarily be realistic in terms of a triangle, but in other scenarios, we may have that this is what the value of sine x is, and yet it's saying, well, now find all of the angle, or all of the values of x for which this works between 0 and 360, and so forth. What we're going to have to do to find these other possible values for the angle then is to potentially be familiar with what these functions look like as graphs, so that just graphically by sketching them out, even roughly, so long as we know the details, we can then see, okay, there's going to be another solution over here. So for this, if we were just to start trying to plot the sine graph, now, as with any graph, you could in theory just plug in some x values, note what the y values are, put them on an axis, and then just try to join them up as best you can once you can see the pattern. But again, if we can be familiar with the shape just offhand, that'd be great. So the sine of 0 is just 0. Making sure that you're in the degree setting of your calculator. The importance of that we'll discuss a little later. Then the sine of 90 is 1. The sine of 180 is back down to 0. The sine of 270 brings us down to -1. And the sine of 360 brings us back to 0. So the reason why, therefore, our graph, we've only bothered to go up to 1 and -1 in the y-axis, as those are the extremes that this graph will go to. The regular y equals sine x won't go any higher or any lower. When you get into transformations of graphs, you could have like sine of 2x and so forth. And if you had to draw that, then it may be slightly differently, but we'll focus on those rules in transforming graphs. As for going up from 0 to 360, as you can see, we've kind of gone through a whole cycle here, and it would then carry on the same on the other side. And also, it's just that's how many degrees are in a circle, right? And basically, it would continue in the same pattern into the negative. So at -90 would now be back down to -1, -180 back at 0, -270 up to 1, and -360 is back to 0. So from this, we can now create a wave function, a curve, which is going up and down in cycles of 180 or a whole period of 360. Now, from this, there may be certain values of sine x that you will be expected to know. Obviously, you will have a calculator, but a question may ask for you to kind of like show out your steps that you're working, and it may rely on you spotting that you should know certain values. So they may expect you to be familiar offhand with the fact that sine 0 equals 0, that sine 30 equals half, sine 45 equals √2/2, sine 60 equals √3/2, and that sine 90 equals 1. Okay. Next, if we were just to move on to the cos graph, just again getting these sketches out first and the known values, and then we'll go into working or how do we then use these to get a solution. Here now again, we'll start from 0, but now cos starts at 1, so 0, 1. It then goes down to 0 at 90, to -1 at the 180 mark, back to 0 at 270, and then up to 1 at 360. And continues on the other side, so down to 0 for -90, -1 at -180, 0 at -270, and 1 at -360. So joining this up again, just in a curve, we end up with a shape like this, which you may notice is basically the exact same as the sine graph. It's just that it's been shifted like 90 degrees to the left. Now what this also means, as you can spot, is that this is exactly symmetrical, that the positive x values and the negative of those x's give the exact same y value. So basically it doesn't matter if there is a plus or a minus for that angle. Therefore, we can actually also describe this function here, the cos function, as an even function. That is to say that the f of x equals the f of minus f. So again, even and what we'll just discuss in a second, odd functions are just something else we could talk about within functions as just being this idea of some kind of way of being symmetrical. So if, like here, a function, it doesn't matter if it's positive or negative, gets the same y value, you can call it even. Sine is then an odd function. That is to say that the f of minus x equals the minus f of x. That is to say when we look at 90 here, that gives us a y of 1. Well, the f of the negative of that x, so the f of minus 90, that ends up giving us minus 1, which is the negative here. So basically, if the minus x value gets you the minus of the y value, that then is described as an odd function. Again, just another term we can use to describe these things as. But regardless, back to just what we were saying before, now that we have this graph, we can also just go on to talk about what expected values we can expect to get. So they may expect you to know that the cos of 0 is 1, that's where we're starting. Cos of 30 is root 3 over 2. The cos of 45 is root 2 over 2. Cos of 60 is a half. And the cos of 90 is 0. And what you may notice here, again, just as, there's already clearly a link between these graphs, but the values for the known sine functions and the known cos functions, these are the same as each other. They're just in the reverse order. So, if you know one of them, you can then just reverse that to work out what the other is going to be. Just a little trick that you can use there. But moving right along, just to get down the last of these main graphs that we're going to be talking about first, that would be that of tan. Now, the tan graph is different to the others because it has something called asymptotes. That is to say, like these invisible lines, that the graph is never going to touch certain x values that will break the function. It would just make them infinitely big or infinitely small. Now, these asymptotes are going to represent by dotted lines, and they are going to occur at 90, 270, and minus 90 and minus 270. So yeah, you'll find if you just like put in your calculator tan 90 or any of those values, you should just get a math error. The value is too big or too big in either positive or the negative direction. But existing between these asymptotes then is the graph. So we're going to start at 0 again, and then we're going to, on the right hand side, start shallow, but then get exponentially bigger, tend off towards the vertical, like the asymptote. And then what happens is it reappears on the right hand side down the bottom, again starting really steep, but then it will shallow off, level off at 180, at which point it will then start shallow, but then become steeper and steeper again, and then reappear on the right hand side of 270 as steep, and then level off for 360. The same then happens on the right hand side, so it's now going to come start off shallow but go down on the right hand side of 90, come back on the top left of it to level off then at 180, come down again before 270, and then come back on the left hand side to level off at minus 360. Okay. For these expected known values of tan then, what you're going to have is, again, tan 0 is going to be 0, because that's where it starts. Tan 30 would be root 3 over 3. Tan of 45 is just 1. Tan of 60 is just root 3. And then tan 90 is infinite, or it's not applicable. NA, there is no value for it. What we can say, though, is just to look back again at the shape of this graph, is that just like the sine function, tan is going to be odd. That if you were to put in the negative x, that would get out the minus y value of what the regular would have been. So if we were to pick like an x value that's about here, let's say about 120, if we were to, that would get you obviously a negative y value here. But if we were then to go to minus 120, that would get you the positive of that same y value. So yes, to put a minus in front of the x is to switch the sign of the y value as well. But then, how does this help us? How does this tie back to what I was saying before about finding the other possible solutions to a given problem? If the calculator, when you do the inverse function, only gives you the x value or theta, whatever symbol you're using, that is closest to 0, how can you possibly find out the rest? Well, let's just, for an example, so we have a reference point, say that, first of all, x is going to be between 0 and 360. And we have that the sine of x equals 0.31, let's say. Well, first of all, we would start off by doing that inverse. We're saying, okay, x is going to equal the sine inverse of 0.31, which, if you just put that in your calculator, is going to come approximately 18 degrees. So if we were to then just find where that is on this graph, so 18 would be somewhere about here, we rise up and go across and say, okay, this is our 0.31, okay? But as we can see, because of how this graph repeats and arcs back on itself, there are more x values on the x-axis that are going to lead to this height. If we were just to continue this on to the right here and then come down, we would find a second x value. Now, how we'll go about working out what this value here is to say that because each of these individual arcs is symmetrical, that however far to the right this one is of 0, that's how far to the left it will be of 180. So, if we say that's like x1, then x2 will be 180 minus the 18, which will leave you, again, because it's only approximate, but around to 162 degrees. Again, if you wanted to double check, if you put sine 162, that should get you approximately the 0.31 from before. Now, in terms of the range that the question gave us, as 0 to 360, these are the only answers we're going to have. Okay, because from just on the right-hand side of the y-axis, because the graph now goes into the negative, there's not going to be another point that is the height of positive 0.31. However, if the question had instead been to be between minus 360 and positive 360, then we would want to continue this line over here into the negative, like so. And then similarly here, continue that further to get that here. Well, how do we then go from these pair of values here to the other pair of values? Well, there's a difference of 360. So now to find just your other answers, we would do 18 minus 360 and 162 minus 360, getting us our total of 4 possible outcomes here. These two other answers then just being minus 342 and minus 198. So, in general, if you're working with sine, what we could say is that your first answer, x1, would just be the sine inverse of whatever the y value was. Then x2 is going to be the 180 minus your first answer. And then any subsequent values are just going to be those first two answers plus or minus 360 each. Right? Just some general rules to go by to find however many answers you have. It's okay to go outside of the range, just just then ignore those answers. But what you don't want to do in a question with saying give every value is to accidentally miss something out, because then you will lose marks potentially. Okay, so then just for a similar example for the cos, if we were again, let's just use that same range of like minus 360 to 360 just to make use of the whole graph. If we were to have, so the cos of x equaled 0.45, let's say. So first of all, your first value would be that cos inverse of your 0.45. This will give you approximately 63 degrees. But then if we were to try to find this on the graph, so let's say 63 is going to be somewhere about here, and that will come across, we'll label this here as our 0.45. But on the right hand side, the next value to also have that height is all the way over here. But again though, due to the symmetrical shape of this graph, what we can say is that however far to the right x1 is from 0, x2 will be that far to the left of 360. So if we were to now do x2 equals your 360 minus 63, that would get you 297, which again we could check if we wanted by just doing cos of 297 and finding that again is approximately 0.45. Then, once again, because this entire graph loops every 360, from this point all you would have to do is then do those previous values minus 360, or if it were going further to the right, you'd add 360. Either way, we now have that you'd 63 minus 360 and the 297 minus 360, which is obviously going to get us minus 297 degrees here and minus 63 degrees here. So as again, because it is symmetrical, we would just have the negative of the previous x values giving us that same y value. So if we just want to draw up some rules again, so for your first x value, that would just be the cos inverse of whatever your y was. Your second will now be 360 minus your first x, and then any subsequent x values will just be those previous ones plus or minus 360 again. As for tan though, again just using the same range, if we would have like so that tan x equaled 0.92, if you were to put that in your calculator first of all, so the tan inverse of 0.92, if we were just to round that to the nearest whole number as we have been with the other ones, that would get us approximately 43 degrees. Yet this time, if we were trying to find that on the graph, so that's going to be about here for our 0.92. Very clearly, my graph is not scale. If to find the next value along with that height, that's going to be here, which is 180 along. The same would go if we'd try to go backwards as well. This is going to be 180 behind it. Therefore, whereas with the sine and the cos we have pairs of values within a loop which then repeats every 360, for tan, all you have to do is take your first value and then just like plus or minus 180. So in this case, that's either going to get us 223 or minus 137 degrees in those cases. So yes, to find the other values in tan is a lot simpler than the other two. All you simply do is say, so your first answer, your tan inverse of that y, following that same format as before, but now every subsequent value, just x1, plus or minus 180, as many times as gets you values inside of that range. But what if the expression inside of the brackets was a little more complex than just a simple single x? What if it was a multiple of x, or again it could be theta throughout any of this, or what if there was some other number that was added or minus to it? Now this does more come under the transformations of graphs, but I would obviously just going to speak about it here because it is intrinsically to do with these specific trigonomic graphs here, although again we'll see the similar principles repeated in that video as well. So what if you do have something instead like sine of 2x plus 10 equals 0.87? Well, again, we'll start off just by doing the inverse here. So but this will now be 2x plus 10 equals the sine inverse of 0.87. Actually, this time, just to make it slightly more precise, we'll now go to one decimal place. So let's say that's going to be 60.5 degrees. Now, following the rules from before, we would find our second value by now doing 180 minus this. And to be clear, that is what we're about to do. But just what I want to stress at this stage is that you should find all of your 2x plus 10 values first before you start rearranging to find x. Don't minus the 10 and divide by 2 now and then carry on with these stages. Do those rearrangings last. Okay, so again, the 2x plus 10 still now also equals 180 minus the 60.5, which is going to equal 119.5. Then, actually, for the sake of this one, let's just return this now to just being in the positive. Okay, let's just say 0 to 360. So at this stage, we would usually now just stop. Because obviously if we just add 360 to this, as would be the next step, we're going to go outside the range. However, when you have a coefficient in front of the x, you should essentially times your range by that number at this stage, right? Just to check how far you're going to go. So because this is 2x, we're actually going to find as many of these values as we can that go up to 720. Because then when we divide by 2 later, that will bring them back inside this range. So, since it's 2x, we'll double the range at this stage. If it had been 3x, we would have tripled it. If it had been half x, we would have halved it, so forth. So, yes, at this stage, we do have room to now add 360 to both of these. So the 2x plus 10 is also going to equal 420.5 degrees by adding the 360 to the 60.5. And it's going to equal 479.5 degrees. To add another 360 to this, however, that would be pushing it too far. That would now again be outside of the 720 limit. So, with these being our 4 values that apply for the 2x plus 10, now we're going to do that rearranging. So to get the x on its own, we'd be minusing 10 from all of these, and then dividing it by 2. So it's going to end up being, so your 50.5 divided by 2, or the 109.5 divided by 2, or the 410.5 divided by 2, or the 469.5 divided by 2. Which of course you would then just actually work that through and get the more precise decimal value. But that would be your x. And again, if you want to double check by plugging in each of those x values in here, you should find they all approximately give you that 0.87. Okay, so that's one example of something slightly more complex inside of the brackets, and that's how we're going to deal with it. Another thing that could change potentially, if we now just shift over to cos to get further kind of practice, is instead, like maybe the function had been squared, right? So let's now say we'll have just x minus 30, let's say, and that is going to equal 0.16. So again, before we can actually get to the inverse this time, before we can get to our x minus 30, we have to make it a singular cos function. It can't have anything else really added to it. So we can't have this square. Therefore, we'll start by just saying the cos of minus 360 equals the square root of 0.16. Now, the problem with this, well, not a problem, but the thing we have to take note of is that when you square root, you have both a plus and a minus answer. Therefore, we now have 2 different things that the cos of x minus 30 is going to equal. Therefore, as we go on to work out what this is going to be, we have to consider that simultaneously it'll equal the inverse cos of plus 0.4 or the cos inverse of minus 0.4. Well, if we were just to then do the cos inverse of your positive 0.4, well, that's going to get you with your x minus 30 equaling, again, let's say 1 decimal place, 66.4 degrees, whereas if you had done it with your negative 0.4, that's now going to be 113.6 degrees. Now we would continue with your regular cos steps by doing your 360 minus that. So in the first case, that's going to leave you with 293.6 degrees, or in the second case, 246.4 degrees. Now then, we can just add over the 30 to get the x on its own, which leaves with 4 answers. So x equals any of the 96.4, the 143.6, 276.4, or 323.6 degrees. And again, it's 4 answers because based on the square root, it's either going to be 2 from the positives on here and here, or 2 from the negative in this middle region here. And while there's no obligation to write them in ascending order, it may just, need to. Okay? Cool. Now I realise this video may be being a bit long already, but there's a couple of other things I still want to introduce to you, just so we get all of these trig graph concepts together. However, these later concepts are going to be from slightly further on in the course, so just bear that in mind as to whether that's relevant for you right now or not. To start off with, I'm now going to talk about something called radians, which is an alternative measurement of the angles. Usually we're using degrees, which is going to be out of 360 for a circle. However, in radians, we have, so if it's 360 degrees in degrees, radians is now out of 2 pi. Now, why this may in any way be beneficial comes more down to the likes of arcs and sectors and so forth, but it may be something we're going to be using here as well with our trig functions. So it's 2 pi rad. Therefore, if we were just to be asked a question in terms of radians instead of degrees, you'll just have to adjust your scales slightly. So it's still going to be between 1 and -1 and so forth here. But if the 360 is now being called 2 pi, then 180 is going to be a singular pi, right? Because it's half of it. 90, which is half of that again, is therefore going to be pi over 2. And the 270, because that's in between the pi and the 2 pi, will be 3 over 2 pi. Then just have the negatives of those on the other side. So yeah, if the question, when it's giving you your range, is giving you a range that's in terms of pi or is in small numbers, you should set your calculator into the radian setting, because that will change things dramatically. Only if it's more like bigger numbers or out of 360, it's more clearly degrees, should you be in the degrees setting. And then again, you would follow the exact same steps as before. It's just that, instead of a 180, you'd write a pi. Instead of a 360, you'd write 2 pi, and so forth. You may then also give your answer in terms of pi, or it may be a decimal once more, depending on what the question is asking for. Okay, so that's just something to bear in mind. So look out for a pi, switch the calculator if necessary, know how degrees and radians may change between each other. And the other thing is then these other trigonomic functions that we technically have, which is cosec, sec, and cot. Now, each of these, if I haven't come across them already, is basically the reciprocal of your regular trigonomic functions. So cosec is 1 over sine, sec is 1 over cos, and cot is 1 over tan, which is why I've also still written them in this order as before. Dealing with solving these kind of functions is something that, as before, we'll just touch upon just in a sec, and also will be talked about in other videos as well. But first, again, let's just start off by trying to draw the graphs, because I feel that perhaps that kind of question regarding the cosec, sec, and cot may be less intuitive if you haven't seen it before. So, to start off with, actually, because, for instance, the cosec graph is related to the sine graph, let's just redraw out the sine graph quickly just to begin with. So again, we went up to 1 at 90, back down through 180, and then again, meant to go down to -1 there, up to 360, and then down to -1 at -90, back up to 180, and then through like that. Now, if cosec is 1 over sine, then at any given stage, you are going to have the y-coordinate of the cosec graph being 1 over the y-coordinate of the sine graph. Now, immediately that's going to throw up some problems, because here we have y being 0, and you can't divide by 0, so you can't have 1 over 0. Therefore, this generates asymptotes, like you had with the tan graph, every time the sine graph crosses the x-axis. There would be one on the y-axis as well, but obviously we already have a line there. Cool. And then the other thing we can say immediately is that at 90, if that equals 1, 1 over 1 is still going to be 1. So we're going to have a point here and a point here. And similarly, 1 over -1, still -1, still -1 here. Now, it's just the other thing that would happen is, as in this interval here, the x gets smaller, dividing by a smaller number gives you a bigger value. Therefore, as we move away on either side of this point, we are now going to get higher and higher cosec values. This is now going to tend upwards. So it's going to be the same over on this side as well. And then the inverse would happen in this negative region, wherein if you're now dividing by a smaller negative number, you'll get a bigger negative number. So that's now going to tend downwards, like so. Therefore, if we were now just to ignore the blue, we would be left with our graph for cosec. It being because the semicircles here appearing at the alternating top and bottom between these asymptotes, which in turn occur at every 180. There aren't going to be any expected known values for these like there were for the sine. What it may just be is that if you had, well, what is cosec 30? Well, if cosec 30 equals 1 over sine 30, well, sine 30 was a half, so it's 1 over a half, which would just equal 2. Right, so just do 1 over whatever the sine of that angle would have been if you need an expected to be known angle. Okay, so in the same vein, we'll now just go over the cos to get sec. So cos starting at 1, down through 90, bottom at 180, back through 270, up 360, and then identical going the other direction on the other side. Again, we end up with this asymptotes whenever the cos graph cuts through the x-axis. So we're now going to have an asymptote at 90 and 270. Again, now exactly like the tan graph on both sides. And as per before, wherever it's a 1, the new graph is also going to be at 1. And wherever it was at a -1, new graph is also going to be at -1. And then, again, as it gets the regular graph, the y gets smaller, the new y values are going to get bigger. So you end up again with these kind of like semicircular curves up and down here, like so. So again, just now remove the green. You are left in the blue with what is your sec graph. Again, that's the exact same as the cosec graph, just shifted 90 to the left, just as how that's the relationship between the regular cos graph and the regular sine graph. Again, if you needed to get a sec of a given angle, just do 1 over cos of that given angle as well, whether that's an expected known angle or you just do it in your calculator. Right? That's again exactly how you could write it in. And then lastly, for the cot, if we started off just by drawing our tan, so we need to put in these asymptotes here at your 90s and your 270s. And then we'll have our graph doing its exponential shape, so forth. So coming down, shallow off, then get steeper, and then shallow off again. Now here though, it's going to end up basically completely flipping. Because, once more, if you have right now the y value being 0, this is now going to become an asymptote because you can't divide by 0. So that's now going to be at the 180 and the 360, just like we had with the cosec graph. But now what we'll say is that 1 over infinity over the asymptotes, that's now going to be 0. So not only have the points where it was 0 become asymptotes, but the bits that are asymptotes are now becoming 0. From here then, again we're now basically going to inverse, wherein if you had 1 divided by a massive number, that's basically going to be on the x-axis, but then 1 divided by a tiny number, it's going to be really big. So we'll start off near this asymptote, we'll level off here, and then that will bend down and come down, tend towards the vertical as we reach the next asymptote. But basically they're going to behave as they have done with all the other asymptotes. It's just now going from left to right, to top left to bottom right. So coming down here, level off at 90, and then come down for the 180. Come up from the top left at the minus 180, level off for minus 90, come down for the y-axis, and then do the same from the minus 360 through the minus 270, down for the minus 180. So now, again, if we just try to move the red here, because it's going to be a bit more left to touch, you are left with, in the green, your COT graph here. And again, as before, any given COT value that you may have to work out, you can just do 1 over that tan value. As for getting between the equivalent pairs of cosec or sec or cot, again, that too is going to be based on the exact same principles as their regular graphs. To get between your points on cosec, if say you had a point which was here, well, that equivalent point is going to be over here, and that distance to the right of 0 is going to be the same to the left of 180. So again, x2 would just be x180 minus x1, and then you'd add or minus 360 to go between the equivalent pairs. Again, same principle here. For the sec, you do 360 minus your original, then add or minus 360. And for the cot, just add 180 every single time. So with that, we may then just want to give an example of how we would solve something a little bit more complicated. Again, this is now more just a regular solving of these reciprocal functions, but just with this added element of finding multiple solutions within a range. So let's say that we are looking between 0. Actually, let's just go back to 360 because that's a reliable range to work between. If we were now to say within this range be given that 2 cot squared theta minus 9 cosec theta equals 3. Again, we're going to solve that for that range. For this, we are now going to be using ideas of identities as well. So if you haven't watched the identity video yet, I suggest you do so kind of in tandem with this, because they are very related. But in general, if we're going to be solving for trigonomic expressions like this, we need it to all be in terms of one singular function or one type of function. Right now we have a combination of 2. We have both the cot and the cosec. To work out how to turn one into the other, the identity we may wish to turn to is that of sine squared theta plus cos squared theta equals 1. Because now if we just want to turn these into versions of sec and cosec and cot, what we can do is individually divide by each of these. So let's say divide by the sine squared. So if we do that, sine squared divided by sine squared is just going to be 1. Cos squared divided by sine squared is going to become cot squared, because from another identity we have that tan theta equals sine theta over cos theta, so therefore cos over sine is going to be 1 over tan, which is cot, so cot squared, and then 1 over sine squared is going to be cosec squared. Or alternatively, if we divide it by the cos squared instead, so sine squared over cos squared, that's going to equal tan squared, and then cos squared divided by cos squared is just 1, and 1 divided by cos squared would give us sec squared. Well, in this case, we're going to look for the one that has a cot squared in it, and we'll turn it into terms of cosec. So what we can do is we can replace this with 2 lots, and then to make cot squared the subject here, if we minus the 1 over, this becomes cosec squared theta minus 1, and then minus 9 lot of cosec theta equals 3. Just to expand the brackets, 2 cosec squared minus 2 minus 9 cosec theta equals 3. But then actually, if we were to redo this in like descending powers of the function and also bring all the like terms together, if we now make it again that 2 cosec squared theta, we'll now do the minus cosec theta, and then we'll say we had a minus 2 here, then we're going to minus another 3 to get us minus 5, and that's going to leave us with 0. This is a quadratic. It's a hidden quadratic perhaps, but it's a quadratic because you've got something squared and a term on its own and then just a number. So if you want, you could make this easier by replacing cosec with like x or something, but either way, you would now factorize it by saying we need 1 cosec theta here and 1 bracket, and then cosec theta in the other bracket, so that they times together to make 2 cosec squared theta. Now, what numbers times together to make 5? Well, that's only going to be 1 and 5. What way round do we want them so that it makes minus 9 in the middle? Well, you're going to want a minus 5 here and a plus 1 here, because then 2 times the minus 5 is minus 10 in the expansion, add 1 brings you up to minus 9. So from here, because you have 2 things that times together to equal 0, one of them must be 0 in and of itself. So you either have 2 cosec theta plus 1 equals 0, well, that would leave us with cosec theta equals minus a half, or you have cosec theta minus 5 equals 0, in which case cosec theta equals 5. We're just looking at these though. If we turn to the cosec graph is either all above 1 or all below minus 1. Minus a half is not a y value on this graph. Therefore, even though we get it mathematically from the quadratic, it is not a value that we can work with. We have to work instead with your cosec equals 5. To solve this, we'll probably now just switch it back to 1 over sine theta equals 5. So in other words, sine theta equals a fifth. And then it's just like what we had on the previous screen, where you do the inverse of sine of a fifth. That would get you theta being approximately 11.5. Or if you then did your 180 minus that, that would leave you with 168.5 degrees. And because we're just between 0 and 360, there then wouldn't be any others within that range. Okay, so again, same principles, it's just this extra step of it being 1 over. You now, if it's this kind of question, you would be using more of your identity ideas that are covered in the other video, but now what we can say is that we can spot already whether or not a certain thing is going to lie on the graph and acknowledge, okay, how would you get from one point to another?